Hi, welcome back to Mechanics and Control of Robotic Manipulator. The last class we have seen dynamic control. So we started with inverse dynamics and you can see dynamic control based on motion based and model based. The motion based which we have seen is PD and PID. The model based which we have seen is actually like computer torque control. In this particular lecture we are going to see the MATLAB simulation on this dynamic control. In the sense dynamic control simulations we are going to see. That too we are going to restrict to only that joint space. So the task space we will see in upcoming lectures, but now we are going to see the dynamic control simulations in joint space. So in that sense we will start what is inverse dynamics. So we know like inverse dynamics aspect, and inverse dynamics will work as a open loop or feed forward control if both initial and you can say initial actual position and as well as desired positions are same, and you can see similar way the initial actual and desired velocities are same and non-zero acceleration are there, then it will work good, right. So that is what we have seen. Then we have started talking about second order aerodynamics is stable. Then we derived what you call computer torque control, which some people call PD with feed forward and feedback linearization control. Some people simply call model based control. Then we have seen actually like a motion based where the acceleration is desired acceleration is not known and the model parameters are not known. Then we can do, provided we assume that if the spatial system, then the gravity need to be compensated, otherwise the system performance may not be as what we expected. So then we can say PD plus gravity compensation or PID plus gravity compensation. These all we have seen. So the same thing we are trying to see in MATLAB simulation. The first thing we are trying to do the inverse dynamic model. So where you can say tau given in the desired values. So m of q desired into q desired double dot plus n of q desired comma q desired dot. If these all known, because q desired dot and q desired double dot are known, so we can calculate m desired and as well as n desired, then we can actually like apply what you call you can say inverse dynamic model. So this is what this is something like f equal to ma, right. So that kind of thing. So for that we are actually like writing a you call MATLAB code, so which is nothing but inverse dynamic simulation of RR serial planar robot. So here we are actually like assuming there are certain variable which are global. So last class, or you can say in the kinematic control class, we have seen L1 and L2 are global. So where that we can actually like use in some of the sub function. Similarly here M1, M2, G and as well as A1 in A2. So instead of L1 and L2 we use A1 and A2. So these are actually like a global. Further, what we assume that the total simulation time here is actually like 12 second and the step size is actually like 10 millisecond and the duration of the total time span start from 0 to TS. So these all we have actually like conventionally see. So now for demonstrating, we have taken one of the same code which we have done in the dynamic simulation, where mass of the first link is 2 kilogram and mass of second link is 1 kilogram, and the length of the first link is actually like 0.5 and the second link is actually like 0.4. So link length, these all actually like we have taken, and then we have actually like gone further, right. So for inverse dynamics, I already said if we introduce gravity, there would be a small you can say hiccup will come. So in order to avoid that, I assume that there is no gravity acting, in the sense the gravity is balanced. So then we need to identify what would be the initial condition. So here I assume that the initial joint position, actual joint position is as equal to desired. So probably when we come to the that part, you can see why it is we have taken as this way. So pi by 3 minus pi by 4 as the you can say theta 2 initial, and why it is actually like taken so and so 0.2 times of pi by 2 as the joint velocity. That we will see in the next you can say continuous slides. So before going to talk about that, so you can see this is the q desired. So the q desired we have taken as a 2 sinusoidal signal. So the theta 1 is actually like varying pi by 2, in the sense it is actually like minus pi by 2 plus pi by 2 with a frequency of 0.2 times of t. Okay. So similarly the theta 2 is actually like varying, so pi by 4 oscillation, but it is actually like varying from pi by 3. So in that sense, you can see like now why this initial condition has actually like come pi by 3 minus pi by 4, because if we take theta like a time is 0, so then the theta 1 would be 0 and theta 2 would be pi by 3 minus pi by 4. The similar way you can see like q dot the side. So if you substitute the time equal to 0, then you can see, so 0.2 times of pi by 2 would be the theta 1 dot and theta 2 dot at 0. That's why we have taken this, right. So now based on this, the q double dot decide, all those things we have used. So further the dynamic model, instead of writing it everything inside the you can say for loop, so we have actually like made some kind of sub function which is EC. So for that we are taking first inertia matrix, which is we call inertia 2R. So which is going to give inertia matrix based on the, you can say q. The q1 is actually like theta 1 and q2 is theta 2. So we can actually like calculate the inertia matrix. In this case, it's a 2R serial manipulator, which is 2 cross 2. The same way we can see other effects which we have written in our lecture, which was V of q comma q dot. So that is what we have actually like written as a subfunction, which is we call other efforts vector. Okay. So now this is also like a depend. So here you can see like both the thetas and theta dots are dependent. So we have you can say call q comma q dot. So similar direction we can take the gravity efforts. Okay, so q would be the input, then we can actually like get the gravity vector g of g underscore v, we can find it. So further, in order to make much more you can say beneficial, so we are using Jacobian you can say subfunction which we derived in the kinematic control. Similarly, the forward kinematics and inverse kinematics of 2R serial manipulator we have taken here for understanding, or whenever required we can use it. So in that sense we will come back, even if we derive the you can say trajectory based on the cubic polynomial, we can use this subfunction which we derived in the what you call kinematic control. So these all actually like subfunctions. So now come back to the original function. So we are deriving the m decide, in the sense the inertia matrix based on the desired value. Similarly, other vector based on desired value and gravity vector based on the desired value we have calculated. So now the first three you can say values are actually like desired. Similarly, the actual inertia matrix, other vector and gravity vectors we have actually like found based on the actual q dot. So now once these all available, so where we can go, we can actually like try to find out what is tau. So tau in this case it is simple what you call inverse dynamics. So inverse dynamics, what it says, the m decide into q double dot decide plus other vector decide plus gravity vector decide. So now we have actually like given that as the input vector here. So then we are going the straightforward numerical integration. So first we find the acceleration vector, the tau minus of other vector you can say plus gravity vector, and this is actually like m inverse, these are all actual, whereas the tau would be having all the desired. So then the velocity would be propagated based on this, and the you can say position update or position propagation is based on this. Then I want to actually like plot something like animated way. So I want to actually like find what would be the actual values. So I am just taking you can say forward kinematics for that, just to show the animation of the forward dynamic model simulation. So now based on this, if we go to the MATLAB you can say simulation, so we will go to MATLAB code. So you can see this is the code which we have actually like shown there. So you can see like this is inverse dynamic simulation of RR planar serial manipulator or robot. So these are the cases. So now we are actually like taking it these all. So here we assume that gravity is 0, later on we will bring it, and here we are not considering the frictional effect because the frictional effect is not exactly model it. So that's why we ignore here the frictional effect. Then we are actually like getting the q dot decide, q decide, q dot decide, q double dot decide. So based on this, so then we are actually like calculating the desired value, based on desired value what would be the dynamic model, and actual value what would be the dynamic model. So then we found the input vector and all the things. So finally we want to plot animate. So we are actually like taking the animated stuff here. Okay. So then we are actually just plotting it, and these are the sub functions which we are actually like shown there, right. So now if I actually like run, so you can see like this is going to be the first theta 1 is actually like going to vary plus or minus you can say pi by 2. So it starts from 0 and it goes pi by 2, then it comes back. So we'll see. Similarly, the other one is it is actually going to vary between, you can say pi by 4, but with addition of pi by 3, and the velocity also going. So right now we take everything is actually like idealistic, in the sense the initial condition and actually like initial velocity and initial position are as similar as the desired initial position, and the gravity we make it actually like a 0. So then we are trying to run. So I'll just make it, this is probably at least so 30 second. So now if I actually like run, so I can actually like supposed to be run this. So if I run this, you can see, so this is what you can see, the theta 1 is actually like rotating between plus pi by 2 minus pi by 2, you would have seen, and this is actually like rotating, this is you can see like a plus pi by 2 and minus pi by 2. The other one is actually like you can see the mean is pi by 3, on top pi by 4 plus or minus, right. So now this is the you can say inverse dynamics. So now if I introduce the gravity, it may not actually like work what we expected. So that what you can actually like see. So you can see, right, it is actually like making it completely different. So this is due to you can see there is a non-expected thing, because the gravity, the compensation is not exactly going to compensate based on the actual, because the propagation model is actually like one step forward, so that we cannot actually like able to predict. So now you can understand why the gravity we consider as 0, or when we do the open loop control with you can say you call inverse dynamics, this is may not be working as good. Okay, and similar way we assume that the initial conditions are not matching. Okay. Okay, just I assume that the initial position supposed to be pi by 3 minus pi by 4 as the theta 2, but now I assume both are 0. So you can see like that may not go as such what he expected. Okay, so you can see, right. So this is actually like going beyond, because the actual scenario is completely different than the inverse dynamics. In fact, if I extend, this may end up with even unstable. Okay, so that's why inverse dynamics as a open you can say simple you call feed forward control, people are not really using. So we started actually like pi by 3, and then we are trying to see whether the system is actually like going, it is not going at all, right. So similarly, if we assume that the initial velocity is supposed to be same, but we assume that it is actually like not given that way. So the theta 1 dot initially there is 0.2 times of pi by 2, but we are actually like assuming that it is not the case. So then also you can see like it is not following the exact profile what we have actually like indented, right. So these all actually like the you call subset, or you call limitations of the open loop control, because there is no feedback, right. So I hope now you are actually like understand. So even you can actually like increase this, probably I am just increasing this in a faster sense. So in the sense I am actually like making it, this is increasing into 0.3 times. Okay, so I am just making it, everything is actually like 0.3. So then this initial velocity also like 0.3. So now if I actually like run, you can see like that would be faster. So but if you look at it, the theta 1, it is not exceeding plus or minus pi by 2, right. So that is what we expected, and that is what happening, right. So this is what the forward dynamics. I hope you are actually like clear to this forward dynamics. Let us come to the what you call the computed torque control. So we will actually like take the same scenario what we have used in the computer torque control. So for that I am actually like considering few other things, where the control parameter Kp and Kd I have assumed as 4 each. Okay. So although we are not using the frictional, but I just consider the frictional value. So in the simulation I will show you, if I consider friction, what will happen. Okay. So now, so this is the control law which we derived in the regular lecture. So we are trying to incorporate this. So for that you need to have the, you can say q tilde and q tilde dot. In addition to that, you need to have the actual vector need to be compensated. So in that sense you can actually like see that. So the Kp into q tilde and Kd into q tilde dot is coming, and then actually like you can say q double dot desired, and this is multiplied with mass and then the other vector plus gravity vector is added. So we are calculating q tilde as q decide minus q, and q tilde dot or q dot tilde is actually like q dot decide minus q dot. So now we will actually like go to the you can say MATLAB code. So this is actually like computer torque control. So we can see like we assume now the gravity is included, okay, and we have taken, there are two control gains are coming, Kp and Kd, so that also we have used, and intentionally I make it that initial joint velocity are not same as the desired, okay. So then we have actually like seen that we have calculated the q tilde and q dot tilde, and then the control law we have actually like used this way, and then based on that we are actually like writing it. So now here we have just added one more. So earlier we have just you can say plotted only time versus q, but here we are plotting time versus q tilde in addition, that's all. So now if we run this, so we can see that the q tilde will actually like go somewhere. So we can see the initial velocity we consider as 0, 0. However, the theta 1 dot decide is something, right? So in that sense, the one, in the sense q tilde 1 would be actually like going upshoot and then coming back, that we can actually like see it, okay. So this is the actual, and it is actually like following it, right? So now you can see this is what I was actually like quoting. So the theta 1 dot is actually like supposed to be non-zero, which is 0.2 times of pi by 2, but we have not considered. So because of that, in order to compensate that velocity profile, so the theta 1 error is actually like going and getting it. However, the theta 2 error is, you can see, almost 0, right? In fact, it is superimposed here, it is like a 0. So now this is the profile which we are actually like asking to follow, and it is actually like doing it. So here we have given probably 45 degree, sorry, you can say not 45 degree, you can say 12, 15 second. So 15 second, in the sense it is actually like making it, so this is 30 degree, or you can say it is actually like up to 30 times, and then this is actually like going somewhere, okay. So if I actually like give this, so 0.2 times of you can say pi by 2, okay. So now you can actually like see that that error would be converge, okay. So I will plot one more thing just for our benefit. So you can see, right, it is actually like so in the order of milli, even actually like further milli radians, right. So this is what the error, you can see error almost 0 both the cases. So now you can see like this is actually like following it. So now I'll just want to plot it, I hope. So the forward kinematic model is available, right? So I'll take it, the forward kinematics here. Okay, so I'll just take it. So I'll just take x decide. So I'll just say, so x decide, I hope x decide, I have not used xd anywhere. So yd, so this is q underscore decide, right, and this is underscore decide, okay. So I'm just plotting it here, okay. So I'm just making it, so here I'm actually like plotting x decide comma y decide, that too like I'm showing that that is the desired plot, which is I'm showing it as k double dot, and this is dashed line. So now if I actually like run this, so I hope this some error, because okay, so here okay. So we can actually like plot this x decide and y decide. I hope this x decide and y decide is actually like derived here. So then we can actually like see, so q underscore decide, right. So q underscore decide 1 comma I, and this 2 comma I. So this makes this, and we are actually like trying to plot this. So now the x decide and y decide is having the same thing. So we can actually like make it this. So there is a, so we can actually like see it here. X desired did not come because it is actually like inside. Okay, that we will actually like do it. The X desired is actually like I just want to show the plot. So, but that is actually like not as explicit here because the forward kinematic model what we have used is slightly different. So now we'll actually like go back to the one which we have actually like tried. So now I will actually like increase the Kp and Kd. You can see that the error value further you can say decrease or increase based on this. So now I am saying that this is 8 and this is probably you can say 16, just I said, right. So this is 2 omega, this is omega squared. So that way I have actually like make it, you can see like it is going to be much further reduce the error, right. So now you can actually like feel it. So now if I actually like introduce the friction, I hope the friction values are here. So now I introduce the viscous friction. So you can actually like see, so this control still working because the friction we have not compensated based on that. So you can see like it is going there, right, because that is what the you can say difficulty or you call constraint on the model based control. So now the model is inaccurate. So because of this inaccurateness, so you can see that the frictional effect we included that actually like not able to compensate here, right. So however, if you add this here, then that will come, that is anyhow feedback linearization, right. So that is the aspect here. So even I add the 0.1 times of the friction total effect, I assume that the friction is actually like very low. So now also you can see like there would be a small error which is actually like propagating because it is not able to continuously follow it. So now we can actually like go back to the what you call the slide. So we will go to the motion based control. So where we have taken PD control with the gravity compensation. So the code only get changed here. Already we defined Kp and Kd. So only thing is actually like the feedback linearization where the other vector removed and Q double dot desired is removed and M matrix also removed. So now the Kp and Kd we need to tune accordingly. So this is what we call the PD control. Similarly, if we want actually like PID control, then the Ki we have to add, and error tilde also like a Q tilde integral error also we need to add. So here we assume that is EI. So EI we have actually like propagated based on simple integration, Euler integration. Then we have actually like got it. So now I will show you this here in the MATLAB code. Then you can actually like see. So this is the PD control. So now we assume that the friction is 0 and gravity is included. So the gravity compensation we have taken, okay, and Kp and Kd we have taken as 4 each. We did not change because your mass is actually like only 2. So it would give reasonable result. If your mass is very high, then we have to actually like tune the Kp and Kd. Right now we need not to actually like do it. So now remaining everything is same. So if I run this PD control, you can see like it would be having a small steady state error, so that you can actually like see it. So you can see like earlier the computed torque control without friction, it was almost like 0 where it is in the order of 10 power minus 4, right, in the sense milliradians. But here you can see it is actually like centiradians at least, right. So that is what one you can say issue. So now if I add the PID control, so where the I term we added as, so Ki and Ei initially we assume 0 0. So then we have actually like calculate the integral error and then we have actually like added this term. So now if I actually like run it, so you can see like this would be following the same profile what we have given, okay, and you can see that the error is actually like very close to 0. Both are actually like converge to 0. Now if I increase Ki or increase Kp, accordingly this will actually like get changed, okay. So this is the benefit of ours. So now even if I add some friction, okay, so for example I am adding a friction, so you can see some different phenomena here. So it is trying to follow, okay. So but you can see like it is not, you can say, propagating like what you have seen in the computer torque control, right? So but here you can see it's still under the control. So that is the advantage of motion based control. So that's why we are actually like trying to what you call combined feed forward come feedback. So that is what the whole idea. So now you can see like even the friction we included, the I term is actually like trying to compensate, whereas the PD control, if I include the friction, so it may actually like give a slightly a similar response what you have seen in the computer torque control. You can actually like see, right? It is actually like trying to go somewhere, right? After that it may get stable or not, that you can actually like see by increasing the time. Probably I said that just 30 second if I ran. So you can see like it is actually like going across and getting it, right? You can see. So it is actually like not able to follow, right? Because it is actually like having a steady state error of so and so, right? So that is what we can see, the steady state error is prolonged. Whereas the computer torque control, we include the friction, okay, and we have run for more time, and we have actually like taken everything is same. So I'll just take it, this is 4,4, so that the consistency will come, okay. So because the 16 may actually like end up with, you can say, unstableness. So now you can see like it is much closer. So now you can actually like see it, right? So now the error is actually like you can see propagated, right? So you can see the PD control with a simple motion based compensation, it is actually like somewhere within this, so within plus or minus 0.05 radian, but it is actually like going across. So in the sense the second state is not able to follow because the other effect vector is actually like a propagating, which is we are trying to compensate. So now I hope, so this is actually like very clear to you. So with that we are ending this particular lecture, but the next lecture we are going to see what you call the computer torque control in task space and the cascaded control loop, which we call dual loop, where the kinematic control at task space and the you can say inner or dynamic control in joint space, that combination we have seen. So this MATLAB simulation we will see. Until then, see you, bye, take care.